So I'm going to apologize for the video because I'm at home and my laptop, I'm not using my board, so it's going to be a little bit rough. We'll just kind of work with it though. All right, so this first one um, is just kind of a review of what we did together last week. I'm going to put on the side here part of your card. Um, oops. If you don't have your card handy, you can just kind of look here. Okay. So remember when you're finding the square root of 45, because 45 is not a perfect square. So when you're looking for the square root, you're looking at this column only. Since there is no square root of 45, you're going to break it into two square roots. This first number only can be a number in this column. Since 9 goes into 45, I'm going to use 9 times 5. And I can take the square root of 9, which is 3, but I can't take the square root of 5. So it's just 3 squares of 5. All right, with the second one, we're going to do the same thing because square root of 24 is not a perfect square. So I want to find the number that goes into 24, which is going to be 4. So this one's a little trickier. You got to keep the 2 in the front, and then it's always times the square root of 4 and the square root of 6. Remember, I always put the perfect square first. It's just going to make the simplifying easier because the square root of 4 is 2. You can take the 2 times this 2 to get 4 square roots of 6. All right, so the only thing that changes here is because it's a cube root, you can only use cubes. So I want to find which perfect cube goes into 24, which that'll be 8. And you got to write the cube root each time. So the cube root of 8 times the cube root of 3, because this number comes from the cube column, and 8 times 3 makes 24. The cube root of 8 is 2, and you can't take the cube root of 3, so it just stays the cube root of 3. Making sure you always keep that cube root inside the corner there. All right, last one for this one. We're going to keep the negative 3 times the cube root. I'm just going to make 2 of them right away. So what perfect cube goes into 250? Look in the cube column. And 125 goes in evenly to 250. 125 times 2. I'm going to keep the negative 3 times the cube root of 125. If you come over here, straight over is 5. So negative 3 times 5 times the cube root of 2. And then you can just multiply the negative 3 times 5, which is negative 15 cube roots of 2. Sorry for the sloppy writing. Okay, this is kind of a key part of this lesson is finding what's missing. No matter where you see some variables, you're going to try and figure this part out. It says if the result of this subtraction is a real number, if the result is a real number, think about all complex numbers are a plus b I. If it's a real number, that means the imaginary number is no longer there. It has a 0 value. So if we want a 0 value for the imaginary part, it would be 4 minus what to make 0 for the imaginary? That means that the bi here has to be 4i. So it doesn't matter what the real part is, so you have to keep the a, because that doesn't matter. It can be anything, plus 4i. So let's just look at how this works out. If I take 10 plus 4i minus a plus 4i, you're going to have 10 minus a, whatever a is, because it doesn't matter. That'll be real. But then you're going to have 4i minus 4i, which is 0i. That's what makes it a real number, is because the b is 0. You're just trying to decide, what do you put here that makes it 0 on this side? And maybe it would help to think of it as this needs to be some real number, it doesn't matter, plus 0i on this side. The imaginary part needs to be 0 for the answer to be a real number. And then for this part, what would the result be to make it an imaginary number? So if you want it to be an imaginary number, that means a has to equal 0. And so 10 minus a has to be 0. So it just means a has to be 10. And remember, the b can be anything. So they're just wanting to know, what would this number be to get an imaginary number on this side? So the real part has to be, the a has to be 10. 10 plus bi, because the b can be anything. So you just keep you always want to have both the a and the b represented. It's just that we need the 10 to be here to make the answer imaginary. So this answer should be a plus 4i, and this one is 10 plus bi. This is the value. This would be the complex number, so that when you subtract it from this part over here, this number minus a plus 4i makes a real number, and this number minus this part makes an imaginary number. Okay, so this part I feel like is a little bit easier. Maybe I'll just use typing to help. First of all, you always combine like terms. So you take real plus the real, and it equals the real. And you're going to take, maybe I'll just put this over here. And then you take imaginary. Probably simplify this a little bit so it doesn't take up as much room. Imaginary plus imaginary equals imaginary. All right, so if I look at letter A, I'm trying to find this complex number to make this statement true. So I'm going to take the real plus the real, it equals the real. So 3 plus a equals 10. So if you subtract 3 from both sides, you get a equals 7. And over here, you have to do the same thing with the imaginary. We're going to take 2i plus ei equals negative 5i. Be careful with your negatives. So then we're going to subtract 2i from both sides. So bi equals negative 7i. So for this first one here, this a plus bi is what I'm going to put up here. The real number, a is 7 minus 7i. Now you can mostly reason through this, but it's very easy to make a simple mistake. So I'd really caution you, especially when you get to the checkpoint tomorrow, is to take your time and write everything out. And remember, you always have to explain everything. All right, so now let's look at letter B. So I'm just gonna draw a line. All right. So if you want to pause the video and try this one first, see if you get the right answer. A minus negative 5 equals negative 6. So if people make mistakes here, when you subtract a negative, this statement is actually a plus 5 equals negative 6. So you have to subtract 5 from both sides. So a equals negative 11. So see how easy that is to make simple mistakes here if you're not careful. All right, then I'm going to take the imaginary. So each time I'm just matching the imaginary minus the imaginary equals the imaginary. Each time you just stick with that every single time. So bi minus 4i equals 7i. So then you just add 4i to both sides. So i equals 11i. So the answer to part B is negative 11 plus 11i. Okay, so when you first learned absolute value, think about what's the absolute value of negative 5. Hopefully you thought, oh, that just equals 5. And what's the absolute value of positive 5? It's also just positive 5. And why is that? That's because absolute value is its distance from 0. How far is negative 5 away from 0? A positive 5. How far is positive 5 away from 0? Positive 5. Absolute value is the distance away from 0, and distance always positive. That's why absolute value is always positive, because absolute value is distance. So with complex numbers, it gets a little bit more complicated, but think of when you graph a complex number, it's on the complex plane. And so we're talking about the distance, not just from 0, but from the origin on the graph. All right, this is just a screenshot. So let me cover up mine. Little dot here. If you're using Desmos, it's probably helpful if you're doing that. Okay, so if I want to graph 3 plus 2i, I'm going to go 3 to the right on the real axis, and up 2 on the imaginary. So I'm going to write this out because this is what I'm going to be looking for when you graph complex numbers, the explanation. So you would move 3, let's say right 3 along the real axis and up 2 on the imaginary axis. That would be your best explanation for your graphs because you need to identify that this axis here, that you understand that's the real axis, it's not the x anymore. When we're talking about complex numbers, the real takes the place of the x and the imaginary takes the place of the y. Okay. Going back to how can we find the distance that this complex number is away from the origin. So just looking at this, do you have any ideas? So I want you to think about, what if I do this? What if I create a right triangle? What do you know about all right triangles? The Pythagorean theorem tells us that a squared plus b squared equals c squared. So we can use this because in our picture over here, this distance a is 3. This distance here, b, is 2. So we can just plug that into the formula over here. 3 squared, which is 9, plus 2 squared, which is 4, equals c squared. So 13 equals c squared. So c is the square root of 13. So when you're doing complex numbers, you just use your Pythagorean theorem using your a and your b, plug it in, and simplify. So if you wanted, what I would do this on Desmos. Just go through your Desmos slides and just check all of your answers and ask some of your cohorts in class if you have questions. And this is just more, just go ahead and submit and you should be able to check on Desmos.